Welcome to The Explainer. Today, we're diving right in, using our slides to break down an idea that, well, it challenges the very laws of our universe.
So, let's get right to it. Is the speed of light really the ultimate speed limit? I mean, we all kind of take that for granted, right? But we're about to explore a text that says, nope. And it argues its case using some surprisingly simple thought experiments, all aimed at one of the biggest, most fundamental ideas in all of physics.
Okay, so before we go any further, just a quick but really important heads up. Everything we're going to talk about comes directly from this source material. We're not here to prove it right or wrong. Our job is just to explain the arguments as clearly as we can so we can all understand where the author is coming from. That's the goal here.
All right, to really get what the author's trying to do with these thought experiments, you first have to understand their starting point. And that starting point is a pretty fundamental critique of physics itself. It all kicks off with, believe it or not, a philosophical disagreement.
And here it is. The argument kicks off with this really provocative claim. Basically, the author is saying that modern physics has just gotten lost in abstract ideas. Their whole mission is to drag the conversation back to what they call the tangible real world.
And this right here, this really shows you the heart of the disagreement. It's like two different worldviews. The author is building their entire case on the idea of a world made of rigid, physical, solid stuff. And that's totally at odds with what they see as the pure energy models of modern physics. You have to get this point, because this idea of a solid material reality, it's the foundation for literally every single argument that's about to come up.
So this brings us to a really key term the author uses, almost infinite speed. Now, they're not talking about a pure mathematical infinity. Not at all. They're talking about a speed that's just so incredibly fast that, for all practical purposes, a signal sent along a rigid object would seem, well, instantaneous.
Okay, so how on earth do you even begin to prove something like that? Well, the author's first major thought experiment takes this idea and scales it up, way up, to a global level. Just try to picture this for a second. Imagine a rope so unbelievably long that it wraps around the Earth 7.5 times. That's more than 300,000 kilometers long, which, by the way, is how far light travels in 1 second. Now, the author's argument is super simple. If you pull one end of this rope, this one single rigid object, the other end has to move, right? And because it's all one connected thing, they claim that movement, that pull signal, would be almost instantaneous. It would have to travel faster than light could cover that same distance.
And get this isn't just some abstract fantasy. The author actually proposes a real-world test for this, at CERN of all places. The idea is, you take a simple cord, wrap it around their 27-kilometer track about 11 times, and then you bring the two ends super close together. The hypothesis? If you move one end, even a super high-speed camera wouldn't be able to spot any delay before the other end moves. To our eyes, to the camera, they would just appear to move at the exact same time, simultaneously. Okay, so that's the rope. For the next proof, the author shifts gears. They move away from a pure thought experiment and focus on a real, actual object that's out there right now, hurtling through deep space, the Voyager 1 probe.
So here's the setup, and it's pretty clever. We all know NASA talks to Voyager 1 all the time. The author's idea is to time those communication signals at two very specific points in Earth's orbit. First, you do it when Earth is moving towards Voyager's general location. Then, you wait 6 months and do it again when our planet is moving away from it.
The whole logic here really just hinges on simple addition. You start with this number, Earth's orbital speed, which is about 30 kilometers per second.
And here's where the math comes in. The author argues that when Earth is moving away from Voyager, you should just add our speed to the probe speed, which is about 15 kilometers per second. So 30 plus 15 gives you a combined separation speed of 45 kilometers per second. Simple as that.
Okay, so what does that all mean? Well, from there, they calculate that this changing relative speed should create a very real, very detectable time difference in how long it takes that signal to go to Voyager and come back. And the big reveal, the predicted result, a full 16-second difference. For the author, this is the smoking gun. If you could actually measure that 16-second gap, it would, in their words, completely destroy the idea that the speed of light is constant.
But the author doesn't stop there. It's not just about these two huge, large-scale examples.
They also point to some much more common, everyday things to argue that, evidence for this theory is actually all around us.
You can see the strategy here, right? The author is trying to build a case from a bunch of different angles. So yeah, we have the big rope experiment and the Voyager test, but they also bring in arguments based on stuff like mobile phones and even laser reflections off the moon.
So take mobile phones. They argue that when you get simultaneous messages from a single satellite, that's a challenge to this idea of non-additive light speed. And with the moon, they point out that when we bounce a laser off it, the reflection doesn't come back to the exact same spot because the moon is moving. For them, this proves that the motion of big objects has a real, measurable effect that they claim current physics just kinda ignores.
And this right here really gets to the heart of what this text is all about. The author's goal isn't to have the final word on anything. It's to use these practical proofs, these real-world, tangible scenarios, to try and force us to look at fundamental physics from a totally new angle. It's really just an invitation to question a core assumption we all take for granted.
So look, whether these arguments would actually hold up under intense scientific scrutiny is one thing. But either way, they leave us with a really fascinating question, don't they? By grounding their whole critique in these simple physical ideas, ropes, spacecraft, the author makes us ask ourselves, what does it actually take to challenge a fundamental law of science? How high is that bar? And honestly, that's a thought worth exploring.